Second sem of first year M.Sc students. We have 5 papers, 4 core courses and 1 elective course. In between this, first we say about course code and then about paper name. First paper code is MAT411 and paper name is Advanced Abstract Algebra second course code is M8412 and paper name is Real Analysis second. Third paper code is M8413 and paper name is Topology second. Fourth paper is M8414 and paper name is Complex Analysis second. These are 4 core courses and last one is elective course. Paper code is M8432 and paper name is Advanced Discrete Mathematics second. Previously, I am telling about the papers and their textbooks and some chapters in between them. For first paper, that is Advanced Abstract Algebra second. There are unit first to unit 5 and we use textbook Topics in Algebra by I.N. Hustin and second textbook is Basic Abstract Algebra by Bhattacharya, Jain and Pal. And in these 2 textbooks we have some chapters for unit first to unit 5. That is, for unit first we use chapter 3 from first textbook, which is ring theory. For unit second we use chapter 4 from again first textbook, that is by Hustin, and chapter name is Vector Spaces and Modules. Third unit from again first book, chapter 6, and chapter name is Linear Transformation. Now in 4th and 5th unit we use second textbook, that is Bhattacharya, and in unit 4 and 5 there are chapters 15, 16, 17 and 18 from this second Bhattacharya's book. 15th chapter is Algebraic Extensions of Fields. Chapter 16 Normal and Separable Extensions. Chapter 17 Galois Theory and chapter 18 Application of Galois Theory of Classical Problems. Now in second paper, Real Analysis second, again there are 5 units, unit first to unit 5, and we use the textbook of Major Theory and Integration by G. D. Bara, and there are articles from second chapter, third chapter, fourth chapter, fifth chapter, sixth chapter and seventh chapter. Few articles are there, not all articles. In chapter second, that is name is Measure on the Real Line, there are articles from 2.1 to 2.5. Chapter third, that is Integration of Functions of a Real Variable, article number 3.1 to 3.4. In chapter 4, Differentiation, there are article 4.1 and 4.3, 4.4 and 4.5. Now from chapter 5, Abstract Measure Spaces, article number 5.1 to 5.6. From chapter 6, inequalities and LP spaces, articles from 6.1 to 6.5. And from last chapter, that is chapter 7, convergence, article 7.1 and 7.2. Now in my paper, that is third paper is my paper, that is topology second, and again there are unit 1 to unit 5. We use textbook of Stephen Billiard, general topology, and chapter 5, chapter 6, chapter 7 and chapter 8 are there in this Stephen Billiard's book, general topology, chapter 5, chapter 6, chapter 7 and chapter 8. Now fourth paper is complex analysis second. Again there are 5 units, unit 1 to unit 5, but there are 2 books for this complex analysis. First textbook is Function of One Complex Variable by John Conway, and second textbook is Complex Variables by Herb Silverman. In this complex analysis second paper, unit first, unit second and unit third from first textbooks, that is by John Conway's textbook. From this John Conway's textbook, chapter number 6, 10 and 11, and remaining units are from from Herb Silverman's book, and chapters in this Herb Silverman's are chapter 10, chapter 12 and chapter 14. Last paper is Advanced Discrete Mathematics second. Again there are 5 units. Also we use 2 textbooks, J.P. Trimley and R. Manohar, first textbook, and second textbook is C.U. Liu, Elements of Discrete Mathematics. Again from chapter 3rd, 4th and 5th from first textbook by Trimley and Manohar, and chapter 6 and 7 from second textbooks, Elements of Discrete Mathematics by C.L. Liu. This all syllabus is available on Telegram group and also on WhatsApp group. In this my paper topology second, we use textbook General Topology by Stephen Billiard, and in this book we have chapters 5th, chapter 6th, chapter 7 and chapter 8, and sections from 17.1 to 27.13. Let us start syllabus of our paper. First we see some definitions in first unit and second unit. That is first unit and second unit from chapter 5. Chapter 5 is complete, that is separation. Name of the chapter is separations and countability. In this first and second unit we will see the definitions: T0 space, T1 space, T2 space, that is Hausdorff space, regular space, T3 space, completely regular space, T3 1/2, that is Techno space, normal space, T4 space, completely normal space. In topological space we use some concepts, and here we use normally, and in definitions we use the open set, closed set and neighborhood. Open set and neighborhood are equivalent concept, therefore in few definitions we use open set, and in place of open set we use neighborhood. Generally, in the diagram, first we take rectangle for topological space, circle for open set, and rectangle for closed set. For T0 space, we use only one open set. That is, for the circle, there is only one open set. This is the trick for T0 space. And for T1 space, then we use two open sets. For T2 space, again we use two open sets, but there is some condition. First we will see the definition of this T0, T1 and T2 space. For T0 space, for two distinct points xy of topological space X, to distinct point, that is, for x is not equal to y, we take only one open set G, that is in topological space X. For two distinct points x and y, there is only one open set containing one point but not the other. That is, x belongs to G but y does not belong to G. Then this X is called T0 space. Another diagram is for topological space X, for two distinct points x and y of this X, there is open set G containing y but not x. This topological space is again T0 space. For T1 space, in topological space X, there are two distinct points x and y. For two distinct points x, that is, x is not equal to y. Two distinct point xy of x, there are two open sets G and H, containing one but not the other. That is, in topological space X, there are two distinct points x and y containing, that is, x belongs to G but y does not belongs to G, and there is another open set H, that is, y belongs to H but x does not belongs to G. That is, there are two cases. First, x belongs to G and y does not belongs to G, but y belongs to H and x does not belong to H. There is another diagram, that is, for topological space X, there are two distinct points x and y and two open sets G and H of X. That is, x belongs to G but y does not belongs to G, and y belongs to H but y does not belongs to G. Now for T2 space or Hausdorff space. In T2 space, that is Hausdorff space, X is topological space and for two distinct points, every pair of two distinct points xy of X, that is, xy belongs to X and X is not equal to Y, there are two disjoint open sets G and H, such that in topological space X, there are every pair of two distinct points x and y of x, there exist two disjoint open sets G and H such that x belongs to G but y does not belongs to G, and y belongs to H but x does not belongs to G, and y does not belongs to H, and G intersection H equal to phi. In this case, X is called T2 space, topological space X is called T2 space or Hausdorff space. Now next definition is regular space. Topological space X is called regular space if and only whenever for closed set A of X but X does not belongs to A of X, there is two disjoint open sets U and V, disjoint open sets U and V, that is for topological space X. There is closed set A of X and point X does not belongs to this A. There exist two disjoint open sets U and V. This is U and this is V, that is X belongs to V, A is subset of U, and U intersection V equal to phi. Then this topological space X is called regular space. Next is T3 space. In T3 space, definition for topological space X, regular T1 space is called T3 space. Regular T1 space is called T3 space. Next definition is completely regular space. Completely regular space. In this completely regular space, again some definition for regular space, that is for topological space X, there is closed set A and of X and X does not belongs to A of X. There exist continuous function. There exist continuous function f from x to I, where I is close interval 0 to 1, such that f of x equal to 0 and f of a equal to 1, that is for function f from x to I is close interval 0 to 1. Here closed set A of x and point x does not belongs to A, then f of x is equal to 0 and f of a is equal to 1. That is, when point x does not belongs to A, then its image is 0, and for image in closed set, image is in closed set, then answer is 1. f of a is equal to 1. Such a topological space X is called completely regular space. X is called completely regular. Next definition is T3 1/2 space, that is Tikhonov space. Tikhonov space. Definition is completely regular T1 space is called T3 1/2 space or Tikhonov space. Next definition is of normal space. Normal space, again for topological space X, A and B are two disjoint closed sets in X, and there exist two disjoint open sets U and V, such that A is subset of U, B is subset of V. And here we know A intersection B equal to phi, also U intersection V equal to phi. For this diagram is in topological space X. For every pair of disjoint closed sets A and B, there exist two disjoint open sets U and V, such that A is subset of U and B is subset of V. Such a topological space is called normal space. X is normal space. Next definition is T4 space. Again, this definition is simple, that is a normal T1 space is called T4 space. Normal T1 space is called. Now we revise these definitions. T0 space, that is a topological space X is said to be T0 space if and only if whenever X and Y are two distinct points in X, then there exists open set containing one but not the other. That is, X for topological space X is said to be T0 space if for two distinct points xy of X there exists open set G such that X belongs to G but Y does not belongs to G. Y belongs to, or second case is Y belongs to G but X does not belongs to G. And diagrammatically this T0 space is, that is in first case in topological space X for two distinct points X and Y, there is open set G such that X belongs to G but Y does not belongs to G. And in second case, X for topological space X, and again for two distinct point X and Y, there is open set G containing Y but not the X. This is T0 space. In the definition, the topological space X is said to be T0 space for the if and only when X and Y are two distinct points in X, there is an open set containing one but not the other. Second definition was T1 space. In this definition, X or X tau is, this topological space is said to be T1 space if and only if any pair of distinct points X and Y of X, there exist two open sets containing one point but not the other. That is, if X is topological space, then for any distinct points x and y of x, there exist open sets G and H such that x belongs to G but y does not belongs to G, and y belongs to H but x does not belongs to H. And diagrammatically there are two cases. In first cases, for two distinct points x and y, there are two open sets G and H such that x belongs to G but y does not belongs to G, and y belongs to H but y does not belongs to G. In second case, in topological space X, there are two open sets G and H. That is, this G and H are not disjoint. They can meet each other. For this two open set G and H, X belongs to G but Y does not belongs to G, and Y belongs to H but Y does not belongs to X. Third definition is T2 space or Hausdorff space. Topological space X tau is called T2 space if and only if every pair of distinct points xy of x distinct, that is x is not equal to y, there exists two disjoint open set. Disjoint means here intersection is empty. That is, for two disjoint open sets of two distinct points x and y such that there are two open set G and H, disjoint open set, such that x belongs to G, y belongs to H, and G intersection H equal to phi. Diagrammatically, in this topological space X and two distinct points x and y, there are two disjoint open sets G and H. Disjoint, that is intersection between them is empty, and here x belongs to G but x does not belongs to H, y belongs to H, and but y does not belongs to G. That is, here this X is called T2 space or Hausdorff. Next definition is regular space. For this regular space in topological space X, this topological space X is said to be regular if and only whenever a closed set A in X and X does not belongs to A. Then there exist two disjoint open sets U and V such that X belongs to U and A is subset of V. Diagrammatically, in topological space X, there is closed set A and this does not belongs to A. There exist two disjoint open sets U and V such that X belongs to U and A is subset of V. This X is regular space. For this regular space, we don't take 2 points, we take one closed set and 1 point which does not belong to that closed set. Next definition is T3 space. Simple definition, a regular T1 space is called T3 space. Now next definition is completely regular space. In this name, first we take regular space and function defined on this regular space. A topological space X is said to be completely regular space whenever A is closed set in X and X does not belongs to A. That is, first property belongs to regular space. Then there exists a continuous function f from x to I, where I is closed interval 0 to 1, such that f of x equal to 0 and f of A equal to 1. That is, this definition concentrate on this closed set A. That is, image of A is 1, otherwise it is 0. This function defined on X. Therefore, this X is called completely regular space. Next definition is technospace, that is T3 1 by 2 space. Definition is simple. Completely regular T1 space is technospace or T3 1 by 2 space. That is, this for T3 1 by 2 space, we have definition. We must know definition of T1 space, regular space, and then completely regular space. That is, topological space is Tiknov if it is completely regular T1 space. Now, next definition is normal space. For this normal space, we take two disjoint closed sets in this definition. Topological space X is said to be normal if and only whenever A and B are disjoint closed sets in X, then there exist two disjoint open sets U and V such that A is subset of U and B is subset of V. Diagrammatically, in topological space X, there are two disjoint closed sets A and B. There exist two disjoint open set U and V such that A is subset of U and B is subset of V, and A intersection B is U intersection V is phi. Such a space is topological space is called normal space. For normal space, we take two disjoint closed set and that set contain in two disjoint open set U and V. Such a topological space X is called normal space. And in this lecture, last definition is T4 space. For T4 space, a normal T1 space is called T4 space. That is, topological space is T4 space if it is normal and T1. It is normal and T1, then it is called T4 space. Thank you. Thank you.